Yeah. No, it's like I was really so yeah, well, after work, another so it's something. And I just like it's like why that's off. And I was like, I can't do it. And I very well with it. So then she was essentially it's like someday a lot of my friends have to flip those. Yeah, we're gonna get back. We're not really saying that was nice. It was
All right. Hope everyone had a nice break. We have a busy 2 weeks this week and next week. So let me just go over again what we need to do. So Thursday, we're going to have a quiz. It'll be 2 FRQs, Riemann sums, and differential equations. We've been doing a lot with Riemann sums, so we're going to review differential equations probably today and tomorrow. And then we have until Thursday to get ready for our quiz. But as soon as we get done with that quiz, we need to switch over to reviewing for our multiple choice test. So next Tuesday will be 8 multiple choice questions over 4 derivative topics. And we'll go over that on Friday and Monday. And then Wednesday and Thursday, we'll prepare for our multiple choice test, which is Friday, but this will be over the spring interval topics. Again, 8 questions. And the test next Friday, the test next Tuesday and Friday will merge together to be one test grade. So quiz grade, test grade this week and next week. And then after that, we're just working on packets 5 and 6 to finish off of those packets to earn individual quiz grades for both of them. But these next 2 weeks will be the last full normal bell schedule. After that, that first week of May is going to be, or that last week of April to first week of May will be EOC, and then AP exams will follow after that. So on Friday, I checked packet 3, pages 1 through 5. And then for tonight, your homework will be to finish off page 6 through 12. So tomorrow, I'll check pages 6 through 12 in packet 3. And then if you weren't here that Friday before break, I'll check pages 1 through 5 as well. All right. Is anyone missing packet 3? We're going to go to page 13. Okay, page 13. Okay, so at the beginning of 2010, a landfill contains 1,400 tons of solid waste. The increasing function W models the total amount of solid waste stored at the landfill. Planners estimate that W will satisfy the differential equation dW dt equals 1/25 W minus 300 over the next 20 years. W is measured in tons. T is measured in years from the start of 2010. And part A says, use the tangent line or use a line tangent to the graph of W at T equals 0 to approximate the amount of solid waste that the landfill contains at the end of the first 3 months of 2010. So that's going to be 1/4 because this is T is in terms of years. So this is 3 months is a quarter of the year. So we want to use a line tangent to approximate. So basically dealing with linear approximation. But to do that, we're first going to have to build our tangent line. So part A, let's find our tangent line. Now, what's different about this problem is that we're seeing variables that we're maybe not as used to seeing. We're used to seeing x's and y's for tangent line equation, but if you see variables that are not in x and y, if it's a word problem, typically it'll be t and something else. T will be your x, and then the other variable will be your y. So we have to kind of just get used to that, some of that notation. It's not always going to be x and y, but if it's not x and y, it'll be time and something else. So our tangent line usually looks like this, right? Usually it's y minus y sub 1 is equal to m times x minus x sub 1. But because the variables we're dealing with is in terms of t and w, our x is going to be our t variable and our y is going to be our w. So let's rewrite the equation so we kind of have some way of connecting to it. So let's say w minus w sub 1 is equal to m times t minus t sub 1. Right? It's still a tangent line equation. It's just we're seeing some variables that we may not use as often. Okay, so to do that, we have to find our point. Our point is going to be t comma w. And our tangent line is going to be starting off at 0. So our point is going to be 0. And W is in terms of tons of solid waste. And we know that that's the beginning of 2010. And 2010 is going to be T equals 0. And we have 1,400 tons of solid waste to begin with. So that's going to be our equation, our point. Our slope is coming from dw dt, right? That's our slope formula. So our dw dt, our slope, and this looks like we need to plug in the order pair 0, 1,400. But it looks like this differential equation or this derivative only requires a w. So we can just plug 1,400 in for w and do the calculation, and that'll be our slope. Because we know dw dt is another way of saying w prime. It's basically our derivative. So we can use our calculator, 1/25. And then 1,400 minus 300. Okay, so that calculates out to be 44. So we have everything that we need to build our tangent line equation. So let me just copy everything that I need here. So w minus w sub 1. Remember, we're replacing, just like how tangent line equation, we're replacing y sub 1, x sub 1, and m in our new tangent line equation with our new variables. We're also replacing the same pieces, t sub 1, w sub 1, and m. And then w and t, just like y and x, will stay as variables. Okay, so now that we have our tangent line equation, we'll clean this up a little bit. But then after we have our tangent line equation, we're next moving on to our linear approximation. And that is where we insert whatever decimal value or value they're asking for to plug in for t. So let me just solve for w, get w by itself. So I can say w is equal to 44t plus 1400. This is my tangent line equation. Either of these are fine, but this is more ready for me to do my linear approximation. So now we'll do our linear approximation. We're going to plug our decimal, or in this case, our fractional value, into our tangent line equation. We get 44 times 1/4 plus 1400, right? Linear approximation is just plugging that decimal value into our tangent line equation. So it's not exact. That's what we call it in the approximation. We get 1,411 tons of waste. So based off of this linear model, the waste that we have plus the rates that is growing, we can approximate that 3 months in, the landfill will have 1,411 tons of waste. Okay. So part A. All right, part B. Find d2w over dt2. That's a notation for second derivative. So we have to find second derivative, but we know that we already have our first derivative. So let me write that out. We just have to make our way to our second derivative. Okay, so we are already at the first derivative level. Let me just clean this up here. If I just distribute that through 1/25 w minus 300 over 25. Okay, so now let's find the second derivative. So d2w over dt2. And we know that the derivative of this, right, we're taking the derivative of this to move to from the first derivative to the second derivative level. So 1/25 will stay. And w will turn into w prime, or in this case, dw dt. And then the 300 over 25 is a constant that drops to 0. Okay, so our second derivative is simply this 1/25 dw dt. And I can replace this dw dt back in terms of what we have originally, right? Just make it a little bit easier for us to interpret. So I'm going to replace this dw dt with this whole expression. These are the same things. Okay, so what are they asking here? So we have our second derivative. Use the second derivative to determine whether your answer in part A is an underestimate or an overestimate of the amount of waste contained at t equals 1/4. So okay, so we know that the W at let's see, what do we know about? Let's see, store. Okay, so our W, right, whether it's 1400 or 1411, we know this is always going to be positive, right? Always positive, because W is, I mean, we're starting off at 1400. So we know that doesn't matter what the W value is. It's always going to be, this whole thing is going to be positive. So it's always greater than 0. Which means that our second derivative is positive, which means second derivative positive means concave up. So if our graph is concave up, then any linear approximation, doesn't matter where it is always going to sit below the curve. And if our graph is below the curve, then any linear approximation is going to underestimate. So we can say since d2w over dt2 is greater than 0. The tangent line is an underestimation. Okay, so revisions coming in. We're in packet 3, page 13. Okay, part C. So part C is kind of like the meat of this problem here, solving the differential equation. So we're going to go through our process, separating our variables, getting our dependent variable on the left, getting our independent variable on the right, cross multiply, and then taking our antiderivative. So part C says find a particular solution. We're going to solve this differential equation. So this looks a little bit different than the different equations that we've seen before in the past, where everything's in terms of x and y. But again, if you don't see x and y, it'll always be time and something else. So now our t is our x and our w is our y. So let's go ahead and get this ready for cross multiplying. I'm going to force this to be a fraction so I can see my diagonals. Cross multiply. And when you're solving differential equations, the parentheses are there to help you. So don't lose the parentheses until after you get full separation. So don't distribute that 1/25 through. You do want to kind of hold on to those parentheses as long as we don't have full separation yet. Okay, so now we want to get separation of variables. We want our w's, or our quote unquote y's, on the left, and then our t's and everything else on the right. So we do see some things out of place. The w minus 300 is out of place, so we do need to divide that over to the left. And one more thing, we don't have to move it, but I think it's helpful. Anything, we want to kind of leave this left side as bare, as minimal as possible. We only want what is absolutely necessary on the left side. You don't have to do that, but eventually everything has to clean up from the left side. So this 25 doesn't have to be on the left. We can move this 25 over to the right side as well. So I'm going to do a double division here, take both of those terms and swap them over to the other side. So now this w minus 300 is going to sit beneath my dw, and the 25 will sit beneath my dt. Okay, we talked about how when you separate when you do separation of variables, you want your dw and dt, or your dy or your dx, sitting up in the numerator, right? We know that they need to be in the numerator. It's okay to have your other variables sitting in the denominator, but these are our anchor variables. These have to be in the numerator. We should be ready for a lot of times your integral rules will either be power rule or natural log. We have to just understand, which circumstances to use. Here, this is a little bit of u substitution. If I can write it this way, 1 over w minus 300 dw equals integral of 1/25 dt. Maybe that helps us see things a little bit easier here. This w in the denominator, this is basically W minus 300. This is our U value. This is going to be a U value to the first power. We can expect natural log. But this is 1/25th. Really, that 1/25th is outside. It's really a 1 dt, which is really power rule. Right? So we may have to go through a little bit of U substitution, but there's not going to be any leftover off of that derivative. We know W minus 300's derivative is just going to be 1, so there's not going to be any leftover coefficient, but we can still go through U substitution here. So we end up with integral of 1 over U du, which we know is natural log. And then replace the U back in terms of W. Meanwhile, this 1/25th dt is really a 1/25th in front as a coefficient, and our antiderivative is really 1, right? So 1 will rise up to be t, so we just get 1/25th t and then plus c at the end. All right, so everything is up at the function level. Now our next job is to solve for W and then to solve for C. And anytime I see natural log, I typically want to just solve for W first. I can solve for C at any moment in time, but I just feel like it's a little bit messy with natural logs in the way. So I'm going to solve for W. I know to get rid of that natural log, I'll raise both sides with E as the base. E and natural log cancels out nicely. We're left with W minus 300. And I can split this up into 2 terms. We know that E to the sum of 2 exponents can be broken up into the product of 2 terms. We know E to the C is just one large C that we can just force in front. Okay, so now I can drop the absolute value because we know this will produce a plus or minus, but then the C will absorb the plus and minus that came from it. So I have W minus 300 is equal to CE to the 1/25th T. Add the 300 over. All right, so now this feels cleaner for me. This is my preference to get it to this point, and now I can solve for C. That's my last step. And the initial condition is 0, 1400. So we'll plug in 0 for T, 1400 in for W, and that should allow us to zero in on that C value. All right, we know that 1/25th times 0 is 0. E to the 0 is 1. 1 times C is just C. So C is just 1400 minus 300, which is 1100. Once you have your C value, you can put it back into the equation where you started making your substitution. Okay, I'd like for us to, for the rest of this class, just to kind of continue practicing these types of problems. I know we took a test on this a couple units ago, but that's our focus today because we're going to see a problem like this, solving differential equations. So, yeah. See if we can get through 2 more, if not 2, if not 3 more of these problems. Okay, page 14. So this problem will follow the same rhythm as the previous one. You're going to get your order pair, get your slope, point slope, get your Bilger equation, linear approximation, plug in the decimal value into your linear approximation. Use the second derivative to determine whether your graph is concave up or concave down. And from there, is your linear approximation going to be over approximating or under approximating? And then part C, separating your variables and then solving for X and taking the antiderivative and then solving for Y and solving for C. Okay, so go ahead and do this problem. I'll work alongside you guys, but I'd like for you guys to see how much you can do on your own as well. Oh, and by the way, this is AB FRQ number 6, which means is non-calculator, which means that you probably don't want to be spending all your time trying to figure out what your decimal value is. You can leave your answer unsimplified, and that will earn you full credit as well. So just keep reminding yourself that you don't have to simplify your answer. In fact, if it's non-calculator, you're encouraged to leave your answer unsimplified so that you're not accidentally making a mistake and then you're losing points when you could have just earned your full points here. But next up is our approximation greater than or less than f of 1.1. We know that they're trying to get us to use that second derivative to help us make that determination. And we want to use our concavity information, right? If it's concave up, our linear equation is going to be sitting below the curve. But if it's a concave down, we know that our linear is going to sit above the curve. So let's look at our second derivative here. In our second derivative, if we plug in 1, 2, looks like it's going to, I don't have to plug in these numbers. I should be able to tell, okay, it's all giving me positive here, right? If I plug 1 in for X, if I plug 2 in for Y, There's no negatives here. Everything is going to be just one large positive number. So I know my second derivative is always positive, which means concave up, concave up. My graph is going to sit below the curve. Okay, part C, now we're going to move into solving the differential equation. So cross multiply, get your y's on the left, get your x's on the right. I'm going to force a 1 in the denominator so I can see my diagonals. Cross multiply to get our dy and dx's lined up in their proper places. We know our dy dx's are lined up nicely. Our decision next is, do we have full separation of variables? Are our y's together? Are our x's together? The x's looks like they're together. The y cubed is out of place, so we're going to divide by y cubed. And it's going to land in the denominator on that left side. Everybody okay there? This is what I see some students struggle with a little bit here. What rule do we handle with this dy over y cubed? We don't need use substitution. It's only one variable. I think it's simple enough where we can just rely on, it's either power rule or natural log. Which one is it? Can I say this? Can I say natural log of y cubed plus c for that? What's the issue here? We only can use natural log if this variable is raised to what power? Y to the what power? First power, yeah. So any other power, we got to bring it up and use power rule, right? So I know that the tendency is students want to use natural log because it's easier, and then they see the variable in the denominator, so why not? But we can only use natural log if it's a variable raised to the first power. Any other power, we got to bring it up and go through power rule. So we can't do this. Okay. So we got to do some rearranging before we can jump into our antiderivative rule. So we got to rewrite it as integral of y to the -3 dy equals integral of x dx. The right side is definitely power rule. This one is no issue. It's just that this y is out of place. We got to bring it up to the top. And now we can, so it's going to end up being power rule for both of these terms. So power rule for antiderivatives, we add 1 to the exponent, we divide it by that new exponent. And after that, we're at the function level. We just have to figure out how to solve for c and solve for y, and those are our final steps. So you don't have to do it in the order that I'm doing it, but typically when I'm at the function level, I'm just trying to find a way to get that left side cleaned up a little more. So a way to do that is, what if I multiply everything through by -2? That way I can get rid of that -2 and kind of force it to the other side here. So if I distribute -2 to every term, that will clean up that left side a little bit nicer for me. And we know that the -2 doesn't distribute to the c. Well, it does, but the c will just take in any constant and just still stay as c. Okay, I'm going to do some cleanup here. I would like to prefer to represent easy to work with variables with positive exponents. So I'm going to force that y back down to the denominator. Right, this feels like a relatively easy spot for me to solve for c. So I'm going to go ahead and do that. One-fourth equals -1 plus c. So 1/4 plus 1 is 1/4 plus 4/4, which is 5/4. So after I solve for c, I'm going to put it back into where I started my substitution. Okay, so this feels a little bit messy here because the y is in the denominator. So one thing that we can't do, we can't just flip every term and make everything reciprocal. It's really this whole thing's in the numerator. So just understand it that way. If we look at it from this perspective, then yes, we can do that. We can flip the left side and then flip the right side. It just looks a little messy, but it's okay to have complex fractions. Again, you don't have to worry about cleanup. You just have to get y by itself, and that's whatever mess it looks like on the right side. As long as it's algebraically correct, it'll earn you full credit. So I can flip this and flip this, but I can't do each individually. I can't flip the y squared and 1 over -x squared plus 5/4. Anytime there's a plus or minus involved, we don't have as much leeway in terms of organizing our terms as we do with multiplication. But we can definitely do this though. We can definitely flip the left and right and flip the right side as well. You can also do this. You can also cross multiply and then solve for y squared. But it's like a over b equals c over d. I can flip both fractions without any issue. And now our final step, take the square roots. But plus or minus shows up, right? But anytime you have a plus or minus square root, you have to decide which one do I want to keep. Do I want to keep the positive square root or the negative square root? And the way you tell is you look at the y value of the order pair. Whatever the sign of the y value is the sign that you want. So the y value is positive. So we want to keep that positive square root as well. Okay, page 15. Okay, so page 15, consider the differential equation dy dx equals 3 minus y cosine x. Let f of x be the differential solution, particular solution to the differential equation. A portion of the slope field is given below. Sketch the solution curve through the point 0, 1. So identify order pair 0, 1 on your curve, and then just follow the path of the graph and just sketch your curve from there. So you're just following the path of the curve. So 0, 1 is here. And you're just kind of sketching the graph along the path that kind of the flow or the stream of this graph here. That's it. I'm going to put part A up here because I want to save, part B up here, and I'll save C for the differential equation. So part A, part B says write an equation for the tangent line. So we're going to find our order pair, which we have, build our tangent line equation, get our slope, and then do point slope form, and then plug in the decimal. So just like the previous two problems, right? Build your tangent line, find your slope, and then point slope form, and then do your linear approximation. Okay, so now that I have my tangent equation, I can use it to do approximation. So f of 0.2. So we take our ordered pair, we build our slope, point slope form, plug the decimal in, and then get our linear approximation. Okay, part C. We're going to solve the differential equations. So cross multiply, right, get our y's on the left, x's on the right. Again, hold on to your parentheses. You don't want to distribute and lose them. They're trying to help us keep our variables separate by introducing those parentheses into our equation. Okay, next up, we have our dy and dx's lined up nicely. Those won't move. But now we have to decide, do we have full separation of variables? And if we don't, what do we need to move? It's the 3 minus y that has to move, all right? We need to move that over to the left side. We want the y's together on the one side and x's on the other side. So divide this over. It's going to land in the denominator on the left side. Okay, now this one feels more like u substitution. There's more than one term in the denominator. They're separated by plus or minus. Let's let this be our u value. And this will end up being 1 over u du to the first power. And this will be a natural log. Okay, but let's go through u substitution because it looks like there's going to be some leftover coefficients that we have to maybe keep track of. There is a negative 1 left over, so it looks like that negative is going to have to stay with our answer. So 1 over u is natural log of u, but the negative will have to stay. And then bring our variable back from our original y variable. So this is the antiderivative of this resulting dy over 3 minus y. And now the right side, I think we just have to remember our integral rule for cosine. We know the antiderivative of cosine is a positive sign, so no need for u substitution on the right side there. All right, so once we find our antiderivative, our integral drops out, our dy dx drops out. We're now at the function level. We do have a plus C that we have to eventually worry about. But we know we have two things left to do. We got to solve for y, and we have to replace c with a numeric value. I'm going to try to resolve this natural log first, but that negative is kind of getting in the way. I do want to raise both sides with e as the base, but I want to kind of get that negative away from that left side because it's kind of messing with my property that I want to use. So what if I just get that negative to distribute and make it go to the other side? So if I multiply everything through with a -1, I can clean up that left side a little bit before I raise to that base e that I want to take advantage of. Okay, e is the base. You know, we can separate this into the product of two bases. We know this is just one large C. Drop the absolute value. We know the C will absorb it. Let me rearrange a little bit to kind of get that y by itself. I would like that y to be positive. So I'm going to move this C over to the left and y over to the right. Okay, so my y is by itself. I like to solve for C now. So the order pair is 0, 1. Zero in for x, y gets replaced with 1, and we can solve for C. All right, it's equal to 1 is equal to. We know sine of 0 is 0, e to the 0 is 1. So 1 equals 3 minus c. C is equal to 2. Now I can put this back into my general equation. Okay, tomorrow we'll continue to put things all together in preparation for Thursday's quiz. But tonight, your homework is to finish pages 6 through 12. And if you haven't shown me pages 1 through 5, I'll also check that as well. Okay, all right, come get your phones.